Stealth, man, stealth. I'm glad I looked at the meeting minutes and or the meeting materials and said, oh, she knows that stuff we haven't. I bet Mary, I thought I would do it. And you did. Yeah, exactly. And you might very well have reasonably assumed that I was going to do that. Hey, Eric, how are you? Lovely, are you? Is DNS working for you? Is DNS working for you? Oh, yeah, absolutely.
Hello, everybody. Welcome to the Tsvarea meeting. My name is Mirja, if you don't know me.
I'm Spencer.
And we start right away with a note well that you may or may not have seen today already, but you should note well that that all contributions here are contributions to the IETF. Let's see what else do we have. And we start right away, basically. We have a packed agenda. We have 2 slots. One is right now, and the next one is right afterwards in the same room, I hope. And these presentations are all clustered a little bit around middle boxes and related to privacy and security. We have, for each of those presentations, we have like in total half an hour. So we have from everybody some slides. We have time for discussions. But we can also have like a big discussion about everything together at the very end. The first 2 documents are basically maybe leftovers from the PLUS work that we did. And we're not planning to have another secret PLUS board here or anything like that. The reason why those are presented here is because we think those are interesting contributions. It's interesting work that have been done. It's both informational documents, but those documents can be very good background input to work that is currently ongoing in the IETF. So our question basically is, what do we want to do with these documents? Because we thought that it might be valuable to have them published somehow. And then we start with the first presentation, Dave.
Hi, I'm Dave Dolson. I'm here to talk about a document that we created in the context of PLUS. So during some of the PLUS discussions, there were a lot of talks about trade-offs of what should be exposed to, in transport layer and whatnot, and we thought it was requested to put the slides are moving.
Yeah, and I forgot the other slides because the order was so weird.
Okay. It was requested, someone should put together a document for, what are the functions provided, and we can discuss them. So we could be on the second slide, please, if you can. Right. So because it was in the context of the transport layer, we limited this to talking about middle boxes that look at the transport layer. So clearly there are a lot that look at application layer features. That is, well discussed at least in the draft MMWG effect encrypt, and there's a lot of discussion there about middle boxes that use or would use application layer data if it weren't encrypted. We looked at different features. We broke them down into 2 cases. One which is just about measurement and what you can measure from traffic. It's mostly TCP traffic currently, and also look at secondly, which devices will modify the traffic in some way. And we also talk about manual troubleshooting. So we look at what you could do with a packet capture in Wireshark, as well as what devices can proactively measure and create alarms about. And I guess we should also say we're coming at this from an operator of a network, from their perspective. So I guess next slide, please. So we saying, when you're an operator of a network, you cannot just say, oh, there's an end-to-end principle. Actually, there is a middle, the network that the packets go over. And as the operator, usually you're the first one that gets called when, video isn't working, or, residential service providers get called for everything. And they need to do some kind of diagnosis. It doesn't work for them to just say, call the server. And also operators use a lot of information to do capacity planning. Do I need to increase the amount of equipment in my network? Do I need to, or where's there's a problem with the network? And they rely a lot on performance metrics. Next slide, please. So I just copy pasted the table of contents here. So because we would like you to read the draft and see what the details are and contribute. These are the authors have come up with things in this list, but I'm quite sure there's more. So the first one, packet loss. Can you detect in your network if your users are experiencing packet loss, right? Can you measure the round trip times of the packets in your network? Can you detect if there's reordering, which may come from ECMP type of issues in your network? Can you identify where the bottlenecks are in your network? Is the packet loss upstream or downstream of a particular point you're looking at? Can you detect if there's a DDoS attack occurring? Can you detect if there's packet corruption? Can you, for example, satellite channel corrupting packets, that type of thing? I briefly we do mention application layer measurements here. This is a context of DNS. So can we tell if DNS is working? Can we tell if what the DNS response time is? So next slide, please. Oh, the slide clicker moved. So I thought it would be useful to just lead through one example, right? So video quality. So let's say you're an operator and a user calls you and says, I'm trying to watch HD video and it's pretty choppy. It's not working. What do you do? So first of all, let's assume we could isolate that traffic, which isn't necessarily obvious either. But you can say, well, are there missing frames coming towards the user? Well, there's some upstream packet loss. Let's do a binary search and see if we can find where the problem is. Are there duplicate frames? Well, that often means there's packet loss or corruption downstream because there are retransmissions, right? Are there reordered frames? We do this, we look at the sequence numbers and say, there's some reordering happened. There are probably multiple paths through the network that are racing each other. That tends to cause TCP to act funny. So are there corrupted frames? We can find some bad hardware or bad links that are corrupting the packets. Are there high round trip times? So there's maybe some kind of buffer bloat downstream. My coworker noticed some buffer bloat of a minute in one of his networks one of the hotels he was at. You can look at the TCP window sizes. If the window is full, this means the client is not reading fast enough from the socket. Otherwise, if the TCP stream looks completely healthy, you can look at, well, the sender is just not writing fast enough to the TCP socket. And this could also be a proxy or a cache that's not doing that quickly enough. Next slide, please. So then in the second part where we talk about the active function, so this is devices that not only monitor traffic, but also do a little bit to it. So the first one's NAT. We're familiar with that. It's changing the port numbers. A firewall, mostly about denying traffic or dropping it. We have DDoS scrubbing features, which are trying to statistically remove the bad while keeping the good. We have network operators doing implicit identification by adding for traffic that's between their customers to their internal servers, tagging it so that the customer doesn't need to log into their own service provider's own servers. Network coding, this is about compressing the data for satellite links, things like that. Network assisted bandwidth aggregation, this is like MTCP for example, done TCP proxy. This is where to make use of multiple links. Some operators are doing differentiated services where they're reordering packets. So, for example, to prioritize, say, voice and gaming above, email and downloads, for example. Some operators are doing, shaping based on different. If you detect a congested network, you can hold back sending some traffic to that network by shaping based on measurement. So it's possible to measure round trip times and do some upstream shaping of the traffic so that to avoid the bloating the downstream buffers. And 3.10, fairness to end user quota. This is a concept that to try to protect the user from overflowing their quota by controlling the rate at which they can receive data. For example, if they're near their end of their quota or something like that. Next slide, please. So an example here. Think about a firewall where very simple policy. I just want to permit only internally initiated connections. So what are some of the things you have to look at there? First of all, most of the firewalls maintain some state about for example, a TCP flow. So they're going to maintain a state on the 5-tuple, source and destination IP address, the ports, and the protocol being TCP. So first thing you say is any packet that's inbound, sorry, that's the third point actually, any inbound packet that doesn't match any state is just denied, right? And you allow state to be created by outbound packets. And typically they are fairly rigid with the state machine too. They'll look for a SYN on the outbound, a SYN ACK on the inbound, where the ACK number matches is sane for the sequence number. Then look for the ACK back to the server, making sure the sequence numbers are sane. And generally the firewalls can be very rigorously protect for I guess a sane connection. But so the tools, I guess the next slide we'll get into. Right, so a lot of the things that we see over and over again in all these tools are the ability to track state, the second bullet, association and confirmation signaling. I think probably Brian will talk about this. But this is, knowing that the responder saw the packet that it's responding to and that it wasn't spoofed by an off-path attack in both directions, so that you know that there's no source address spoofing. A lot of applications track sequence numbers and acknowledgement numbers. This is for finding retransmissions and missing packets and reordering, those type of things. Looking at the acknowledgements, you can get some round trip time information by looking at timestamp echoes and things like that as well, looking at the packets. And also the receive window. So when it comes down to it, there are applications that look at all of the TCP headers. The only one I couldn't find a use for was the urgent pointer. Next slide, please. And also there's a few of these are actually being actively worked on at the IETF. There's a buffer bloat's a big concern. People are trying to address that, and being able to measure that it's happening, I think is important. And that's, DDoS detection. There's working groups involved in that. So again, being able to measure this is happening, being able to mitigate it, these are important features. Network assisted bandwidth aggregation is also something that IETF's been working on. Next slide, please. So to wrap up, we think it's clear that there are valuable functions based on observations at the transport layer, and it actually makes the network better for the users. So, and we're trying to socialize these. So that's the purpose of this document, is to give a perspective and get some feedback on, have we collected the correct features? Have we described them properly? Are there others? We do say something in the security section where we pose the question, is it, more secure if you make a network that can better do security functions? And also we kind of think about the question of whether, what measurement hooks like these should be provided in protocols. So thinking about that going forward. And I think that's the last slide. Or is there another one? The last one.
Last slide.
Okay.
So
I thought I asked about what to do with this document. You don't see it. Okay. So also, what to do with this document?
So just to level set for a second, I think it's good for us to remember that what we're talking about here is what somebody's doing, not what somebody should be doing. And I hope that makes a difference to the conversation.
This is Ian Sweat from Google. Thanks for starting this work. But so I have a few kind of comments on the kind of scope of the work and how it's kind of. I need to kiss it. Okay, that's a little awkward. Thanks for starting this work. So some of the network features you listed, some are unique, some are in IP, some are in TCP, some of them are also in UDP. So it'd be useful to kind of separate out like what things are on what different layers today and like how that's structured. Another is that some of the monitoring aspects you listed are, I think, a little bit conflated with one another potentially. For example, like there are multiple different ways to measure bandwidth, and is the one question is, do you care about bandwidth or do you care about how the bandwidth is getting delivered? Like, RT&T and bandwidth seem useful, but some of the other numbers you're talking about passively monitoring, I can't quite like grok about how that's actually useful as a thing to measure. And then the other thing, the final question is, I think it would be really helpful if you're going to make the statement that it is clear that functions and everything, that this is helpful, to have, especially in the performance section, some data to back that up in multiple different cases. Because I think we're operating in kind of a data void world, and without some data to inform whether it's useful in certain circumstances, I don't think we can really judge that.
So, so you three points, I guess you made. So first one, multiple layers. So we were trying to talk about things at the transport layer. So basically, we're talking about TCP, which with IP, TCP IP.
Okay.
The addresses are part of the 5-tuple. I think some of the other stuff you said, are you interested in helping us improve the wording on the layering and the
I was hoping to just give you general feedback, but I mean, I do think it'd be good to kind of get a little more clarity on what the actual things that are critical to measure are and are not. I mean, that's something we're grappling with right now in Quick. And, if I can help get clarity on that, then I would like to do work in that vein. But that's, I guess, the final question is, of the things that you're measuring, what is actually critical and what's not? And I have no context for that. And if you could provide more context about what people actually use and how many people use it and how critical it is to debugging and such, that would be very helpful. So as a counterpoint to actual performance measurements, like, is this really useful? Is this actually used on a day-to-day basis? Would be incredibly useful.
Yeah, I think there's one answer there is that it's actually fair. The troubleshooting tends to be ad hoc sometimes, right? Stuff's not working. Where do we start? Let's look for some different KPIs and see if we can guess where the problem might be. That's there's some of that goes on. So, is it useful? Do I absolutely have to have round trip time? Maybe not, but do I absolutely have to be able to see window size? Maybe not, but added together, they add more evidence that help an engineer diagnose a problem. And there's also, things, you might see a chart. Oh, round trip time has been increasing over the past few weeks. What is that? And I guess it's useful because we noticed it and it caused us to look into it. But okay, point taken. How do we, definitively say, 9 out of 10 operators use this? I don't know.
Lars, I got so the implicit assumption here seems to be that there's only one way in which these measurements can be taken, and that's yes, Scott. Wow, this is really uncomfortable. I hope you brushed your teeth, Ian. There seems to be an assumption that the only way in which this information can be provided to a network operator is through middle boxes, and that's actually not true, right? So it would be useful to differentiate. So for which of these metrics you've identified there, what are the alternatives, right? We're talking somewhere else in the IETF a lot about in-band telemetry, right? You can probably get a lot of the same measurements in that way or others, right?
Are you thinking, for example, at an endpoint reporting these type of
No,
things?
you're a network operator. You have a bunch of boxes, right? You can find out about the traffic by looking at, I guess, SNFTP or Yang or whatever, or do in-band telemetry or inject traffic, so there's other ways in which you can get the same information that help you troubleshoot what's going on. And I'm sort of reacting a little bit allergic against this assumption that we need the middle boxes to do any of this. We might need them for some of this, and it would be good to find out which of those things you list where we have no alternative to get that same information. For a lot of them, we have alternatives, I think.
So what is taking the measurements? I don't understand if it's not a box in the middle. I mean, maybe the middle box word is wrong here, and I also tried to say that if you take a packet capture, you can do some of this as well.
You could look at counters on a switch,
On
for example,
what?
right?
On a switch.
Just
Okay.
to put this in scope again, I mean, this is documenting what's done currently, and I think this is what we need to have the discussion you just proposed. We need to figure out what's done currently, and then from this point we can start the
So
discussion.
I disagree that all of this needs to be done currently with middle boxes. So some people might do the middle boxes, but
So
others
it's not
aren't.
about needs to be done. It's like this is what people have implemented in their
Okay,
in their firewalls or in whatever.
But
And
it sounds like that this is trying to make the case that we need middle boxes to do any of these.
no, that was not the
Okay.
point here.
Hi, Tom Herbert. So on point number 1 there, improve the network for users. I think from an application point of view, when I send packets into the network, I really don't know how those are exactly improving those packets. So we may have a firewall, we may have NAT, we may have various things. But I do know from an application point of view, the more I encrypt in the packet, the more I hide from the network, the better feeling of security I have. So I'm wondering, how do we balance these two out? Because, so we know when we turned up TLS, many of the mobile operators, they were complaining. Now they can't tell we're sending cat videos and they can't optimize for that.
This may be actually slightly out of scope for this draft.
But I noticed you said that you have a better feeling.
Well, I'm
about
just questioning point number 1 about whether it's clear this is actually improvement.
I know, but I
I think it
noticed.
probably is, but I'm not sure.
I noticed you said you have a greater feeling about security, but you didn't say you had a greater feeling that the packets were going to get where they're going, or you didn't have a greater feeling that it's going to work. Like that.
Right, but
So,
that's,
I mean, I think it would be
that's
interesting.
networking, that's layer 3, and a lot of this is doing layer 4, which the network shouldn't care about. From your point that it's an end-to-end protocol, right?
And I think as an application, from an application point of view, you really want to be able to trust that the network abstraction works, right? You want operators to be able to provide you with a network that works. Therefore, they need some ways to solve the problems. So, I've been thinking about it myself. How to justify this or how to explain this, and I think maybe now's not the time to get into this, but ask the question. What am I revealing that is important or that I care about?
So we have 5 minutes for this discussion.
Yes, as somebody who's done a lot of measurement passively about things like TCP dynamics and stuff like that, it is valuable to have that information. I would like to warn you to be cautious about language about performance enhancing proxies. Because one way of thinking about a performance enhancing proxy is it covers up bugs in buggy implementations. But if both ends are actually modern TCPs, the performance enhancing proxies almost always hurt. We have crossed into that region actually with the first known data point in that space was more than 10 years ago when auto-tuning first rolled out. That the performance enhancing proxies then were doing things like rewriting receiver window, and you don't need it if you've got auto-tuning, et cetera. But the point is they cover up bugs that are likely to become irrelevant, and then they cap everybody else at some state in the technology.
It was pointed out to me that performance enhancing proxies don't always behave properly, but it's kind of like saying buggy routers don't always forward your packets. So I didn't, anyway, I don't think you should say buggy ones or, anyway, it was pointed out to me that performance enhancing proxies was
The key thing is the end systems are actually moving faster than the network. And so putting technology in the network to help certain obsolete end systems is actually a net loss.
Eric Rescorla. So when this presentation was introduced, it was introduced as a descriptive presentation. But this is pretty clearly a set of normative statements about the benefits of these functions. And I'm actually quite comfortable with the draft that says this is what people do. But when you get to the point of saying these are benefits, that seems like a much stronger set of statements. In particular, a number of the things you're describing that these implementations do are adverse to the user in various ways. Traffic discrimination, blocking various kinds of network activity the user actually wants to engage in, those kinds of things. So I think be careful about framing it the way you're framing it as a net benefit to the user. I think it's fine to frame it as people do these things and they have these reasons for doing them.
I can tell you that a lot of people doing these things do believe they're doing it for the benefit of the user.
I appreciate that, but the users may not agree with them. And I can tell you,
So-
I can tell you as someone who tried to roll out new protocols that many of these things interfere with those things, and the users do want the new protocols. So as I say, I think it'd be fine if you phrase it descriptively, but I think this framing of it's actually good for the user, like, I don't think there's anything like consensus on that point.
Well, I think if the network operator can make my video work, that's a benefit. And I think that if the network operator can make my gaming traffic race ahead of some download, I think that's a benefit.
Yes, but it's not a benefit if the network operator, for instance, decides that the kind of traffic A that I want to be doing should be degraded with respect to the kind of traffic B that I want to be doing less. And these devices are used for precisely that kind of traffic discrimination. So it's really disingenuous to suggest that the network operator's judgment of what traffic I want to behave in certain ways is the only judgment that matters.
Gary Fairhurst. As a transport guy, I want to transport packets, and PEPs is a rather big word. They cover a whole range of different functions, whole range of operator functions. If you just want to move bits around and you don't care what they contain because you just care about privacy, that's one thing. If you want operator networks that deliver good performance, especially over radio bearers of various types, you need these devices in some form, and you need the operational tools to know if they work. I once played with a big IPsec network. Not be able to see any of the packets made me effectively unable to manage that network and run it. There's two sides to the story.
Yeah, yeah, some performance enhancing proxies. I think the kinds we were trying to focus on did not modify the application layer. They were more about spreading out the bursts and maybe quickly retransmitting some packets that would otherwise have to travel a long distance. So yeah, I probably should have said that. I would like to clarify that if it doesn't already say that we're not talking about video transcoding and things like that.
Eric Klein, I think you did mention network coding in one of the slides. But if you go back to slide 7 as well, I think if we're going to, on slide 10, anyway, on slide 7, yeah, there we go. Sanity checking, yeah, slide 8 also has it too. Slide 7 has it as well. Deny non-sane packets. If we're going to document what it is that people currently do, absent value judgments, can we also say that the definition of sanity is not consistent across all middle boxes?
That's possible.
And can we further say then that this is sort of the source of one source of ossification in the network?
So definitely cut the line. If you are super quick, you can still.
Ben Schwartz, Jigsaw. if this document is meant to be a value-free assessment of how these boxes are currently used in the network, then I think it's important and clear that that description should include the way that these boxes are used for repressive censorship in networks all over the world.
Jake Holland, I had a related point I was going to. I noticed in the security considerations it says that there are a bunch of uses that are currently done which are specifically excluded from this document. If you're making a document that is documenting the current practices, then I don't know, like maybe, yeah, I think it's of a piece with the reframing of the benefits and just talking about what is actually done. I don't know if you're doing that in a separate doc, but +1 to the value judgment.
Okay, yeah.
Yeah.
So if you read this, I may have put more value judgments in the slides than in the document. If you're reading this and you think the word I've tripped up and put inappropriate value judgments, let me know, because that's, yeah, you can try to. I mean, clearly the title says it's beneficial, but we do think that these help operators. Now, I think that the trade-off is, where, to what extent do you want to help the operator versus, privacy and things like that. I don't know. I probably should stop talking. You want to move on, right?
Yeah, we want to move on. Thank you very much. Thank you for the discussion. I would like to encourage more people to read the document and give feedback to the document. I want to add one more point. First of all, there is this other document that's on this slide here that's talking about the effect of increasing encryption, which is also talking about middle box functions. I think the point about making this more value-free is well taken. However, I think the scope here was to describe what the operators think the benefits are, because like they pay somebody for this box and they think that there's a benefit, and exactly this part is what you need to know as well. Why do they using those boxes?
Perhaps aside from being value free, as it could inventory some of the pros and cons as a middle ground.
So I think that actually the pros are more interesting here, because the question is, why are operators motivated to use those boxes and pay money for it? And if they see a benefit, and then we should find a way to give them this benefit in a different way if this goes away.
Fair enough, but that a lot of people don't understand the risk, for instance, of ossification. And that one really needs to be highlighted at various levels in various ways.
I think so. That's a discussion I'm hoping to have based on this document, based on what we have as a basis for discussion in this document. There's ongoing discussion that will happen that we can do here in TCP area, but it's also happening in other working groups. But just have to have a common basis to see what we talk about. I think this document, so I personally think it's valuable. But if you have a different opinion or further feedback, just go to the mailing list and send your feedback there. Except you have like a very quick point, Aaron.
Here's a quick point. I just want to say that PEPs came up in the TCP SAT working group, which is now 21 years ago. And we published an RFC called Advice to Subnetwork Designers, which was basically how to avoid sins of omission and sins of commission if you were building different kinds of networks that looked unusual compared to the mainstream. This is starting to look kind of like a similar opportunity to do some education for network operators. Like, you may think this is helping you, but here are some risks that you should think about, and maybe look at this. The IETF is getting an education in terms of why people put these things in here and how they help. But I think that we have an opportunity to say, here are some things that you need to consider and how this could turn out to be hurting your customers or making your customers unhappy, or hurting your business in the long term.
So that's definitely more work and probably the next step than just documenting what's out there right now.
Yeah, that document was actually a lot of work, but it was really helpful.
Yeah, absolutely. So we now have to develop presentations.
Yeah, actually, so next we have Brian talking about state management in middle boxes, trying to approach this from a protocol independent point of view, and he's a remote presentation, and I have also no idea how to start that. But I bring up the slides now. We or
No, he's not in queue. Brian, could you be in queue? Okay, there we go.
Hello. Check, can everyone hear me? Do we have audio? Okay, that sounds like a yes. Shall I begin?
Yep, go ahead.
Okay, hi, I'm Brian Tremble. Coming to you live from Zurich, which is not an actual city in Switzerland, not a meeting room. I'm going to talk about a little tiny part of sort of the something that Dave alluded to a bit, was the need for many of these boxes to keep state. We looked at how that works and sort of wanted to figure out how we could do that in a transport independent way. So do I have slide control, or do I just say next slide?
I think you have to say next slide.
Next slide. So here's the problem. There are a lot of devices on path that keep state. Most of these, I think by population, are probably NATs and firewalls. Almost all of them assume TCP semantics and don't work very well with non-TCP transport. So they have sort of TCP, then DNS, and then everything else. If you're going to run UDP transports across these, you need some sort of frequent keep alive. You need to make sure that you're going to refresh your state, because the standard sort of idle state timeouts for these, there was a paper about 6-7 years ago on IMC. Standard idle state timeout for these are hours long for TCP and seconds long for UDP. You might need explicit directional rules and port mapping if you're going to be able to figure out, well, I mean, I'm a firewall, I have a rule that says, okay, well, I want to let inbound SYNs, right? Well, you can't really see a SYN on UDP. You might need other nasty hacks, or in the worst case, there's a box on the path that gets in your way, and you fall back to TCP. So Ian, who I see my camera is pointed at, hi Ian, gave a presentation, I think in Tsvarea about a year ago, about the blocking that they were seeing on Quick, and that came to be, on the order of 5%. So the idea is that all of these devices are not going to go away. They are going to keep doing something with UDP transports. I mean, the large-scale deployment of UDP transports is going to lead to engineering of new devices that are going to try and do smart things with UDP transports. So we should probably define something sane for them to do, because otherwise we might end up with them doing relatively insane things. So, next slide. We took a look at sort of what most middle boxes do with respect to TCP state modeling, and not all of them are going to have exactly this state machine inside them for looking at a single, or for looking at a two-sided flow. But they're going to have state machines that in some way or another reduce to this one. So you have, you have a flow in the closed state, and you see a SYN in one direction, and then you're in the, okay, I'm waiting for a SYNAC state. And then you see the SYNAC come back, and you say, okay, well, I've seen the SYNAC, so now I actually need to know that we're, we really want to have a discussion. And then you see the ACK come back, and you get established, and then you can close that down either by seeing the FIN-ACK and ACK-FIN, or the reset, which dumps you straight back to, the closed state. So we decided to genericize this on the next slide. So this is for those of you who are in the Quick meeting in Seoul, we presented a very early version of this idea. We've gone on from some of the feedback we've gotten from that and made this better. And here we have essentially the state transition sort of along the top side. If you go to the next slide, are handle sort of one-way flows and one-sided devices, right? If you put like a one-way UDP flow through this thing, and you're going to see a bunch of traffic going in one direction to the other, and okay, it's going to go, oh, hey, I have state for this flow, but I never saw a packet come back in the other state until it hits a relatively short-term idle timeout, then it goes back to the zero state. This is what these devices generally do with UDP traffic right now. But we added a few other states to the state machine so that we could actually do something that looks kind of like the TCP state modeling. So next slide. over here on the right side, we have, so this is kind of a genericization of the tracking the SYN-ACK part of a TCP handshake. And it involves essentially two signals, which we call the association signal and the confirmation signal. An association signal is what a server would send back to a client saying, yes, I actually would like to talk to this person who's trying to, or to this node that's trying to initiate communication with me. And then the confirmation signal comes back from A to B, which provides essentially proof that the node at A actually saw the association signal that was sent to it. So this is the return routability proof. This is what keeps sort of UDP backscatter and high volume DDoS garbage from driving the state machine forward. Once you've seen some traffic in one direction, an association signal coming back from the server, and then the client essentially says, okay, hey, I confirm, you're in the associated state. The benefit of the associated state is that you have a longer timeout. So the idea here is that we can reduce the amount of people live traffic that we need for UDP transport. On the next slide, we see this is a little bit different from how things currently work with TCP. This is instead of sort of like the half closed and closed state, we have sort of a stop, wait, and stopping state. And the stop, wait state comes when one of the nodes says, yes, I would like to shut down this connection. And then the stop confirm signal is a signal that encodes two things. One, I'd like to stop this connection. Two, I actually saw the stop signal. The point of this is to the point of this two-way stop is to make it impossible for an off-path attacker to inject a packet that rips state down on these devices and forces them into sort of back down to this lower timeout state. It's a little bit difficult to model this with TCP the way that we have it right now. So this is a slight change to the way things work right now. So next slide. Have a look at the draft. This is the draft Trammel plus statefulness. It's basically got two audiences. One we'd like to consider it as input to protocol design, especially for UDP-based protocols. Really the message here is to consider which messages are made publicly available by the protocol and how those are going to be used to maintain transport state on path. If you have something that looks like an association signal, something that looks like a confirmation signal, and something that looks like stop and stop confirm, then it's possible to build the same middle box that will actually manage state. If those signals are signals that can somehow be reduced them or not available, then you're back down to essentially short timeouts for state management. We'd also like this as guidance for middle box design if it actually goes through and gets published. The idea here is we'd like to point out that it's a good idea to separate the extraction of the signals from the semantic treatment of those signals for state maintenance. And here it's like, okay, well, we have this association signal and this confirmation signal. That's not really an associated bit or a confirmed bit. It's something that can actually be extracted from the packet. And for different protocols, that can be done in different ways. The reason I wanted to talk about this in TSV area today was to ask next steps. Are there people who are interested in seeing this work going forward, and how should that happen? So thank you very much.
Thank you.
Hi, it's Jake Holland. I noticed in the draft it looks like maybe I'm not sure if I quite got it, but does the association implicitly assume that the packet is part of the same bidirectional flow?
So yeah, there's in the draft there's like this other sort of signal. It's the hidden signal. It's the one that associates a packet with a flow. So for the NAT and firewall use case, you pretty much always want to associate these on 5-tuple bidirectional flows because that's what drives the mapping. And
I'm specifically asking for reasons of multicast. Like, would it be possible to use, say, an IGMP packet or MLD packet to construct a reverse path state?
Yes, absolutely.
Something
right. As long as there's enough information in that packet to figure out, which thing you need to associate the state for the later packets on, then yes. And that's the case with IGMP, I believe.
Right. Okay.
Yep.
Eric Pasquala, what do you see as the relationship of this to Quick?
So I see that actually Quick, as it is right now, already provides most of these signals. I think it would be,
Please continue.
yeah, it already provides most of these signals. I think it is generally useful that when that a UDP-based transport protocol can sort of get out of this short idle state, right, into the state where you don't have to basically keep reestablishing state. There's actually another thing that you could do with the design of Quick, which is the fact that you can always quickly resume. It doesn't actually matter whether or not you have short state or not. And then there's a question about state churn, and if this state, so for example, in certain mobile networks, this state's actually kind of expensive to establish. So there might be a benefit to not having to reestablish that sort of along the path, as opposed to the endpoint state. If you can design the transport protocols, the endpoint state is cheap to resume. You still haven't necessarily solved the problem of the on-path state being not necessarily cheap to resume based on the link.
Sorry, I think I may not ask this question the way I meant to ask it. We're not designing a whole lot of new UDP-based transport protocols right now. We're designing basically one and a half, if you count ICE as a half. And so the extent to which Quick doesn't conform with these things, then it's very odd to be simultaneously publishing a document exhorting people to conform with them. And so I guess my question is, do you believe this document and Quick should come into alignment in some way? And if so, what would be the way in which that would happen?
So the two things that are actually currently under discussion in Quick are something like actually your PR20, right? So the way to expose the fact that a connection is going away basically gives you the stop and stop confirm signals. And as far as I can tell, the current header in the 0.2 version already provides enough information, because you can look at the version negotiation part of the Quick handshake, and that gives you the establishment signals.
Sure, I guess I'm still apparently asking it the wrong way, because I'm not actually trying to make a point about the technology.
Yeah.
I'm trying to understand how you think these relate to each other in terms of whether you think it's fine for them to disagree, or whether you think that these eventually have to align, or it's silly.
Oh, yeah, they eventually have to align, or it's silly, sorry.
Mia Kulevind is one of the authors of this draft as well. So first of all, we presented an earlier version of this draft in Quick, and I think it's fair to say that it informed the information about what we're currently doing in Quick as like a basis for discussion. And the other point we have is that in the manageability document, it would actually be, so I think because those signals are very basic, and as Brian explained, you don't have to implement all the signals. Like if you only implement part of the signals, you get only part of the functionality, but it's still the same signals. And I think those things that we're going to expose in Quick are very well aligned with this draft. And the benefit we will have is for the manageability statement in Quick that we can just refer to this draft and say this is the more generic model here, and that's the part that Quick implements and how to use it.
But of course, if we think that we are only going to do one UDP-based transport protocol in the next 20 years, which is certainly a possibility, then yeah, you could just essentially take a tiny part of this draft, suck it into the Quick manageability statement, and you're done.
Right. Well, because I didn't mean to say that. I just meant to say that presumably Quick does represent the IETF, will represent the IETF consensus about which of these signals should in fact be exposed.
Right.
And so that's all I was trying to say.
Right. Okay. Yeah. Yeah. So actually, another way to do this is you could actually make these. You could take this sort of at the middle box design guidance, and you could actually put that into the manageability statement in Quick. That would be another way to do it.
Yeah, like we had this presentation because we were hoping for some feedback how to proceed with this document.
Yeah, if it's do it in the manageability statement in Quick, that's feedback.
This is Ian Split. I had one more follow-up comment about the FIN signal, or connection close signal. I kind of keep bringing this up, but like silent close, either intentional or otherwise, is very much a thing on the internet.
Right.
And so, does the close signal need to be explicit? Is kind of a question worth asking about this, or could it be explicitly time-based, or could it be baked into the, I know this is protocol foo, so a 5-minute timeout or a 1-hour timeout is appropriate, rather than an explicit close signal.
Right. So actually, do you have data about how much TCP silent close you guys see? Like where something just goes away?
In theory, we do, but I don't know.
Yeah.
Maybe like Chung or someone's here.
That would be super useful to have, right? Because if this is a thing that almost never happens, then there's a pretty good indication that you need to do some other silent close. And if it's a thing where silent close just happens about 20% of the time and the internet's fine, then yeah, we don't need to bother with this.
I'm aware of some of that data being present in some of the errors because we see it as errors.
Mm-hmm.
And it's oddly geographically distributed, which makes one suspect that it's a particular group of manufacturers that do it.
Like a particular group of
manufacturers,
middle box manufacturers that are dropping the fins or what? Yeah, okay. Yeah.
Code is hard.
Okay, thank you so far.
Cool.
And I think we move
Thank you.
on to the next discussion or presentation. And that's a remote presentation again. So Diego, can you go into the queue? Go.
Hello.
Yeah, we can hear you. You can start.
Okay, now I can. Okay, so I guess next already. Next slide, I mean.
You can start. We can hear you.
Yeah.
Next slide. Sorry, I didn't hear that.
Yeah.
We can hear everything except next slide.
Oh, that's what I said. Okay, thanks for having me here. I feel a bit overwhelmed with all the technical presentations before mine, but I hope I am kind of helpful from the legal policy side. So my name is Diego Naranjo. I work for European Digital Rights, which is an association of associations. So we are, since last Sunday, 35 civil rights organizations from all across Europe, and understanding Europe in the broader sense of the Council of Europe, so the 47 member states, not the European Union. And our common goal is to defend human rights in the online environment. Yeah, next slide, please. Next. Yeah, thanks. So yeah, just very quickly, a bit about the human rights framework surrounding the e-privacy regulation, which is the main topic of my discussion now. So the right to privacy, as you know, is both in the UN Declaration of Human Rights, but also in our own UN Charter of Human Rights in the European Union, which is called the Charter of Fundamental Rights. We have two distinct rights recognized: the right to privacy and then the right to personal data. Next, please. So the charter is binding in the European Union, is part of the primary legislation for us, and that gave birth, let's say, to three different pieces of legislation that we have now. One is the Data Protection Directive from 1995, the same year what we call the Police Directive, so how the law enforcement agencies can access our personal data. And then later came the e-privacy directive. And now these three elements are going to be replaced by the General Data Protection Regulation, which I will call a GDPR from now on, and the new Police Directive, which replaces the previous one. And we are discussing now the e-privacy regulation. For those outside the EU, the difference between directive and regulation is that the regulation is directly applicable. Next, please. Next, yes. So yeah, the e-privacy was created to complement the Data Protection Directive. After 7 years, the internet exploded and developed developed in a quite stable manner. And so there was the need to have an instrument that covered all this development online and that covered specifically the right to privacy, confidentiality of communications, and data protection issues in the electronic communications sector. So everything that we do online currently. Next. And so the European Commission, which is the body of the European Union that has the right of to propose legislation, published a proposal the last month of January. Overall, we believe that the proposal is a good step forward, but unfortunately, there have been some changes already. There was a leak last December, which was way stronger. But we are afraid that there was a lot of hardcore lobbying from some segments of the industry, and that was watered down and to the text that we have now, which is already quite good. Let's say it goes a step forward into the right direction, but it needs a lot of fine-tuning. The overall discussions right now are quite passionate, and the discussion just started, but even it was said publicly that the e-privacy regulation was going to be the end of the internet as we know it, according to some advertisers. Next. So I put here in a sort of comical way that what is the status of the debate. So telecoms want to join online advertisers, publishers, and no other data subject farmers. And they're saying, okay, the GDPR, which is, by the way, the piece of legislation which we hated for 4 years. Now we like that a lot, that we believe it's the right framework. And well, we believe we need to use the rules that already exist, to use big data, to do profiling, because that's the way we can create the jobs and promote innovation. Some policymakers are now with this new buzzword, which is the free flow of data, and everything that goes against the free flow of data, whatever that means data protectionism, which is the other buzzword they created. But fortunately, the biggest part of the European Commission says that, well, they believe in privacy, they believe in the need to strengthening confidentiality of communications in the new online environment, and they are asking for support from the civil society and other people who are interested in strengthening this law. Next, please. Regarding the text, well, as I said, we believe that we need this instrument, that we need this the e-privacy to complement the GDPR in the era of the Internet of Things, the era of massive surveillance, in the era of online tracking, and more e-communications between our fridge and our toaster and our tablet and our smart device and whatever. We believe we need to harmonize this across the EU, so the regulations are the right choice. It is not about cookie notices. The industry, advertising industry mainly, is saying that there is the cookie law. All these annoying banners you see when you go online, you need to accept and all of that. We say it's not about that. It's about privacy and secure communications. And this is the only piece of legislation that we have right now covering. So we need to keep it and make it better. Some telecoms, for example, Telefónica from Spain, they are going to this business of profiling because they want to compete with other big data businesses from across the Atlantic, from my side, so from the US mainly. And finally, the threat that we always have is, of course, governments. When all of this is being discussed, we hear law enforcement agencies saying that, well, okay, encryption is fine, privacy is great, but, well, we need to catch the bad guys, so we need our exceptions for national security, and we might have to have the master key for all of that. So that's one of the risks. Next, please. More in detail, for us, the e-privacy is an issue of trust. The last NTIA report showed that almost half of the citizens in the US refrained themselves from using certain online activities due to the privacy and security concerns that they had. We saw this also happening in the European Union with the last Eurobarometer, which is a sort of a questionnaire that has been sent from European body to all citizens, well, to a quite big number of citizens to see what they think about, and they're also quite concerned about privacy in the online world. We believe that the e-privacy needs to cover new actors such as the so-called OTTs, so Skype, WhatsApp, and the new methods of communications that we find currently. And also we need to keep the focus on tracking. So it's not about cookies only, it's about device fingerprinting and any other sort of tools that exist now or that can come up in the near future or in the distant future. And that can be used to track citizens. Then is the issue of the cookie wall. So when you go to a public or private website, and then you want to access the information, they say, okay, do you want to be tracked by me or by this third-party advertiser whom we don't know anything about, and do the data whatever they want to do with it? Yes, okay, then if I accept to that, I go to the website and I can access the information. But if I feel like I don't want to do that, they say, oh, sorry, you cannot access, or you will not have the same level of experience in the website. So we believe that there's not a way that banning this sort of cookie wall. Finally, well, not finally, but the issue of privacy by default, of course, and by design by default is it's obvious that needs to be backing the privacy. That was in the leak from December that I was mentioning before, but that has been changed to a sort of privacy by option. So the Commission thinks that now the browsers are still the only gatekeeper to the online world. So when you install your browser, they will ask, okay, how much privacy do you want? Do you want a lot of privacy? Do you want a bit less? Do you want a bit less? And this sort of a few options, and you will be able to choose which one you want. But we foresee that's going to lead a certain website to say, okay, you have a great, you want the highest degree of privacy, but if you have that on your browser, we cannot give you the best experience on our website. So please choose the least privacy-friendly option. So again, that needs to be taken out. We need privacy by default. And there's some omission to collective redress by consumer and human rights groups. And that seems to be a sincere omission. They just forgot to put two numbers in one of the articles, but we are fighting to have that back. Next slide, please. And I have some questions for which I don't have the right answers yet. So the e-privacy currently allows for data retention laws. There was a data retention directive that was invalidated by the European Court of Justice, but it still allows that some member states have them, and they actually do have it. So are we gonna repeal that article, or do we want to add some clarification to that article? That's not clear what's the best approach. And then the OTTs, we want them in the text, but they are saying that if they are in the text, because of this exception for national security, public order, and all of that, they will need to provide access to law enforcement agencies. So all these end-to-end encryption apps in like a Signal or WhatsApp and all the others, they will have to build a backdoor for governments. Third, what's the real alternative to free services? So the services that you use when you pay with your personal data. If people don't want to pay for them, as this is the case currently in the EU, as we have seen in some recent research. And as I said already before, law enforcement agency keeps saying that we need access to devices. We need access to encryption. We cannot allow all of this because of terrorism and child protection and whatever they say at each moment of the year. And so that's another issue that we need to tackle. Next, please. Well, yeah, that's it. Okay, so questions, comments, please. Thank you.
Thank you very much. And there's a question coming in.
Hello, this is Klaus Nieminen from Ficora. Actually, a comment and a comment for everybody. Well, I think especially in addition to the privacy directive, there are, of course, different rules for the ISPs. In the TSM regulation, there are the net neutrality rules. There are rules that the ISP shouldn't monitor the specific content, and the better guidelines have been clarifying that further. That basically, when you're doing this kind of the reasonable traffic management, the basic traffic management ISPs are doing, well, they can see the IP header and transport protocol layer header, but not going deeper to the packets. So it gives also a lot of privacy. So just wanted to add, because I think this is quite a relevant information for these folks, I mean, in the IETF and transport area. Thanks.
Another chance to ask questions or give feedback to somebody who's actually involved in policy making in this space. Okay, then we can just move on to the next presentation, which is also related to privacy. Thank you, Diego.
Thank you very much.
Thank you.
And then our next presentation is Mike.
Who's actually here?
And your setup.
Okay. Yeah, so I'm Mike Perry. I'm with the Tor project. Uh-oh. Yeah, maybe I should do that.
Yeah, just take it.
All right. How's this? Is that a little bit better? Okay. All right. So I'm Mike Perry. I'm with the Tor project. And I'm basically here to talk about the Tor project's perspective on privacy and also traffic analysis for encrypted protocols. Next slide. So I'm going to start off with a quick Tor overview in case people aren't familiar or deeply familiar with Tor. First of all, I guess a quick survey: how many people are familiar with the Tor and the Tor project and feel like they have a solid understanding of the Tor protocol? All right, so that's the hands go down at that point. All right. So then I'm also going to cover a little bit of application layer privacy. We've done a lot of work, obviously, with Tor browser and study changing various behaviors of the browser. Well, I'm not going to get very far into that. I'm going to try and keep it focused to the presentation and session layers, specifically quick HTTP2 and a couple of examples there. And then I think I want to spend most of my time talking about traffic analysis, attacks, and defenses, which is something that the Tor project has recently started encouraging the academic world to study, and that we've been working towards implementing defenses of our own. So obviously, my interest here is to raise awareness of how Tor looks at privacy from a technical perspective, and also generally spread awareness of traffic analysis. So I mean, it's great that since Snowden and now with Trump, there's been this huge push to basically encrypt all the things. And I'm personally really happy about that. I assume most people here are really happy about how that's been progressing. Unfortunately, just blindly throwing encryption on top of any arbitrary protocol doesn't always get you all of the confidentiality properties that you might expect. So I want to go into a little bit of what that looks like. And then I guess Tor is kind of a small organization. You can go to the next slide. So the third goal is sort of like get people inside the IETF to advocate for Tor, because as Tor is a very small company. We only have 20 full-time employees, $3.5 million a year budget. It's not very easy for us to be in all the places where protocol design is happening. So having people take something away from this presentation and help spread it along will be very useful for us. So quickly, the Tor network and how it works is a TCP overlay network. It's actually run largely by volunteers. There are 7,000 relays in the network. It provides a stream abstraction to applications that use it as a SOCKS proxy. So basically, you make a connection through the volunteer-run network by connecting to a local SOCKS proxy that a Tor client on your local machine provides. About 2 million people or clients use the Tor network daily by our metrics, which you can view at metrics.torproject.org. They're not the same users every day. They come from different types of applications using Tor. We have about 1 million users that seem to update the Tor browser within a week, which Tor browser is our probably the single largest Tor application that we make. It's based on Mozilla Firefox ESR. And there's about 5 million Android installs of Orbot from Google Play, in the Google Play Store, and it's not clear exactly how often those people use Tor and to what extent for their applications on Android. Next slide. So as I said, the Tor relay network is TCP overlay network, 7,000 relays in it. This diagram basically shows how the encryption setup is done in Tor. It's what we call telescoping encryption. X, Y, and Z are Tor relays, run again by volunteers. C is the client here, and then the blue tube going through the center is application, application data. The client first makes a TLS connection to the first relay X. Then inside of that TLS connection, it does a handshake to establish an AES key with relay X. Then through that tunnel, it does the same process again, making sure that the two relays have a TLS connection between them, and then negotiating a session key with Y, and then through that, it creates another layer to Z, and then there's TLS again from Y to Z, and then that data can either connect to a public website, or you can actually have two of these what are called circuits connected end to end to connect to an internal address inside the Tor network, which is called a hidden service or an onion service. There's some multiplexing that also happens here. So you can have, because the stream abstraction, you can actually have multiple streams on this encrypted path, this encrypted circuit, and then you can have multiple circuits inside the TLS connections between the client and the first relay and in between relays. Next slide. So some additional terminology that we use when we talk about application privacy. In general, linkability is simply the ability to associate one user action in one context with that same user's action in another context. So you can have linkability in, for example, you might be familiar with the private browsing mode. That's what the PBM is in that use case in browsers. Generally, people expect when they're using private browsing mode, they expect not to be logged into the same sites as they were when they were not in private browsing mode. That's a common use case of this in browsers. There's also third-party linkability. So when you're visiting, CNN.com, and it has the whatever advertisements and Twitter and Facebook like buttons on there, those third-party elements are present on that site, and then they can be present on also the New York Times, for example. And their those third parties' ability to determine that you're the same individual user is third-party linkability. And then there's also fingerprinting linkability, which is the act of using user agent characteristics and computer characteristics to determine that the same user you have the same user even without the usage of identifiers or any state in the client. There's been a little bit of confusion in some of the documentation that I noticed a couple of years ago at the W3C. There's some blurring between the idea of fingerprinting and identifier storage. I think that a better terminology for identifier storage is, the super cookie, rather than blurring various ways of using the cache or TLS state or other statefulness of the browser. That's not really fingerprinting. That's just a form of building identifiers out of state that's in the application. And then fingerprinting, it will be any stateless vector of determining properties and building up of the ability to identify a user. So the way that we approach identifier-based tracking is this, at least in the browser, is this idea of first-party isolation, so that when the browser is storing state or managing connections for a particular resource load, all of that is bound to like effectively a container or a storage mechanism that is keyed and isolated by the domain in the URL bar. Next slide. So I'll have another image about that when we get a bit deeper into that. But in terms of the abstract privacy and anonymity issues that we deal with, obviously traffic and integrity and confidentiality, which a lot of you're all familiar with here, just encrypting traffic and making sure that it can't be modified and it can't be observed, its contents can't be observed. Linkability sources, as I got into, was state management and browser fingerprinting, and then sources of traffic analysis. Those would include basically fingerprinting traffic, looking at traffic patterns to try and encrypted traffic patterns to try and determine what the resource that is being accessed was, even though the contents are encrypted. Correlation, which in the case of Tor is looking at the traffic patterns entering the Tor network and trying to match those up with the traffic patterns exiting the Tor network. Confirmation is the act of having some prior information or some active capability where you are then using that information or active capability to monitor and inject traffic that you can then say, okay, I'm watching this particular set of users and I think it's probably one of them, and I'm going to try and induce a bunch of traffic to the particular user I'm interested in, and then see which of that smaller set of users actually has that traffic pattern. So sort of using multiple pieces of information to confirm a suspicion. And then you can also do traffic analysis through route manipulation and analysis of round trip times and these sorts of things. Next slide. So with respect to that first party isolation idea and the whole idea that we try to provide in terms of how the user conceptualizes what we're providing with them, we want the user to generally have a relationship with each first party, similar to they would have a relationship with their applications on a phone. Basically, if they have a login at Twitter, the fact that they're logged into Twitter should not be visible to CNN, and they should have control over their ability to end that relationship by clearing identifiers and removing site history for that particular site. So where has identifier storage come in the protocols that we've looked at? Now, again, I'm not saying that these are problems with HTTP2. These are just because there is now storage being maintained by the presentation layer. These are things that we have to consider and manage to meet that model of the privacy properties that we're trying to preserve by isolating it. So things like the alternate service header that says that HTTP2 is possible, that if that is cached, we don't necessarily want that property to be cacheable between different first-party domains so that you can't build super cookies by having like, 1 through 32.example.com having different states for HTTP2 availability and then building a 32-bit identifier from those different states of HTTP2 availability. So we would want to isolate all of those, all of that information to the URL bar domain, so that 1 through 32.example.com have different notions of HTTP2 availability depending on whether they're loaded from CNN.com or NewYorkTimes.com. And similar considerations for ALPN, NPN, and the server push response caching. All that sort of needs to be isolated to the URL bar domain for us. Next. Basically a lot of the stuff that was in HTTP2, the zero ITT state caching, which also comes up on TLS 1.3, and the discovery mechanisms. The connection identifier is another thing that we would want to make sure is reset for third parties in different contexts. Maybe congestion information, window information, if that's cached between different visits, those sorts of things. Next. So also fingerprinting is without the ability to identify a user without there being actual identifier storage going on. And the way that we've tried to look at this deep rabbit hole of problems is by just classifying where the user agent information is coming from and what that means in terms of its general identifiability for narrowing in on a specific user. We feel like that the most identifying aspects are when the user configuration details about the computer are exposed to, for example, a remote website. And this is actually, there are CSS media queries that can allow websites to see what the user's desktop theme colors are. So like obviously that can be highly identifiable if you have chosen a very unique color scheme for your desktop. Then, below that is device and hardware characteristics, like specific information about the USB devices that are attached, game controllers that are attached, obviously Bluetooth and wireless networks that might be in range of the user agent. Below that is less severe than that is the operating system version differences. So we don't really like it if you can accurately determine that you have particularly like Windows 7 versus 10, for example. We're a little bit less wary of the ability to determine if you have Windows versus Mac OS versus Linux, simply because there are a lot of different ways to do that as well. So, and there's not a lot of information to there if you're only dealing with the 3 platforms. User behavior, slightly less concerned than OS. Simply, we tend to address that through things like quantifying timestamps for events, so that you can't do keystroke fingerprinting as easily, can't do mouse movement fingerprinting as easily. And then lastly, the last category, browser and vendor and version differences, we completely ignore, from the position that you simply can't make, for example, Firefox look like IE or IE look like Chrome. Basically, you want to minimize the variance of your features within the population of Tor browser users, but you can't really make Tor browser look like any other arbitrary browser of your choice. So we don't do things like user agent spoofing for that reason. And then the ability to fingerprint user is obviously highly dependent on the user base size. So, the more users that you have, the more source of information you need in order to completely segment that user base and identify a particular user. As far as it's mostly relevant to this group, there's not a whole lot. Things like the timestamps in in Quick might be an issue. I mean, they are encrypted, but the fact that they're visible to the server, if there is clock drift from the, or clock delta from the user agent to a canonical time store or source, that could be a problem. And then maybe if there is information that you might be able to infer based on how Quick behaves.
Clarification on the timestamps. So the timestamps are all relative to each other.
Okay.
At some point you zero them out. It doesn't really matter when the zero happens, as long as they're all unsigned. So you can't express a negative time.
Okay.
But you could start at like 1 billion seconds, or, well, yeah, I think 1 billion seconds even would be fine. But clock rate, yeah. So if there's some issues that are very characteristic, it would be identifiable.
Thank you. And then local link property inference that you can tell if Quick behaves differently in its congestion protocol, if it's on a Wi-Fi or Ethernet link. I don't know if that necessarily does, or if that is even planned, but I could see something like that maybe coming up. Similar with how the congestion control behaves. And then for HTTP2, there were things that are fingerprintable if you're thinking about how does Firefox's HTTP2 stack behave versus Chrome's, but that's again out of scope, as is the fingerprinting the TCP stack itself, because Tor terminates TCP. So there's wasn't really a whole lot of fingerprintability that we found there.
Just out of curiosity, what do you do about DNS?
Oh, so DNS is it's sort of tunneled through Tor. We'd only support A and quad A records, and most of the time it's optimized out. You actually are connecting to a host name that the exit node resolves for you, doesn't tell you the IP address, and then proceeds with the TCP handshake. So most of the time it's not there. But that does mean that we right now do not support natively, text records or serve records, and things that might be useful for certificate transparency, for example. We're still trying to figure out exactly how we want to do that. Okay, so traffic analysis is relevant to folks here. Again, there's confirmation and correlation end-to-end. That's mostly more of a Tor problem that might come up with things like turn servers, or if anybody here works on VPNs, maybe that might be an area of interest, but I'm not going to talk too much about that. VBR audio fingerprinting, though, I think probably is relevant, and that there's a study done in 2010 on the ability to use the variable bit rate to classify different phonemes and sequences of phonemes of encrypted traffic. And that paper found that about 256 bits of padding those frames covers most cases. There's a follow-on paper that found, well, you can still sort of classify the language being spoken and maybe some vague, very unique phrases with that.
Hey, Mike, Eric. So currently Tor turns off all these functions, right? In terms of WebRTC in Tor browser, right?
That's right.
So your assumption is that the use case here would be somehow would be snooping on calls made through Tor, or eliciting calls from the endpoint through Tor to you?
No, I just wanted to highlight this because we have been doing a lot of traffic analysis research, and this is something that I've noticed.
Yeah.
Our use case for WebRTC, if we were to support it, which we don't, would be to try and do things like calls over hidden services, onion services, without leaving the Tor network.
Yeah, I imagine the performance that is going to be so terrible that we need to this is going to be the least of our problems, because you won't be able to talk to anybody. It'd be like talking to someone on the moon. But
right, I guess it depends on the codec. We use what's it called? Mumble, TCP based. It's for game like server chats. I use that over Tor, and people use it over hidden services. You can do voice over Tor. Probably can't do video.
And latency is still pretty terrible, right?
It's highly variable, but the Tor network has actually grown tremendously since Snowden, and we haven't picked up an equivalent number of users. So we've gone from like 2,000 relays to 7,000 relays, and we've still floated at that 2 million user mark, and maybe even lost a little, I think, due to Cloudflare. But
I'm just thinking at speed of light, right? I mean, because we usually think even going through a turn relay, we consider to be a pretty aggressive, performance degradation. So I'm thinking 3 turn relays is not going to have the impact you're kind of hoping for. But okay, thanks.
Then that's with Tor as it is too. Like if we were to try and support hidden service-based calling, we could do shorter ephemeral hidden services that have shorter paths, and there are latency optimizations that we can do with Tor. We actually have a distribution over what our expected latency characteristic is over the entire network, and we can actually say, okay, if you want the fastest X% of the paths through the Tor network for this circuit, we can do that for you. I mean, technically, but obviously it's not something that we've implemented yet for that specific case. We just do it as a general case for picking the top 80% of paths for all circuits, all paths to the network. Okay, and then website traffic fingerprinting is the main set of problems that have caused Tor to move into looking at defenses for traffic analysis. This is basically looking at just one end of the traffic and entering into the Tor network, and trying to throw a classifier at it, at those traffic patterns, and then determine what web resource or web page is being accessed. In the general case, it is of just trying to classify all of the traffic coming into Tor. It's likely not feasible. But if you have prior information that a specific site might be being visited, or if you have at a particular time, or if you have information that, oh, this is a hidden service site, you might be able to have higher accuracy. This was studied for just regular HTTPS in the paper Side Channel Leaks and Web Applications that looked at various ways that interactive web applications expose information through the fixed length records of TLS. And they found that about 256 bytes of padding indicates many cases, but it's highly sensitive to things like the number of pages that you're looking at, obviously, and their variability in terms of their size and the types of resources that they're loading. And the Tor's 512 cell size did help us for quite a while, and still it is an advantage for us against this problem. But the literature has shown that it's by itself is not necessarily enough if you have a small set of pages that are probably being accessed. Next. So how do you determine whether or not one of these attacks is something you should actually be worried about? One of the things that we had, the issues we had when these attack papers were coming out, was that the inherent publication bias in academia caused, first of all, attack papers to be favored over defense papers, because they were generally easier to write, easier to justify. And second of all, there are a lot of, you can bias your results and make them look good by sweeping certain things under the rug, by experimentally examining only very small world sizes or sets of pages that you're trying to classify. And you can make an attack look very dangerous when, in fact, if you actually tried to apply it outside of a lab setting and against a large set of traffic, that attack would just fail. And the thing that makes it, the two things effectively from machine learning that make it fail is the base rate fallacy and VC dimension, which is also related to the bias variance trade-off. Basically, the intuitive way to recognize why this is a problem is, for example, an HIV test. If you had an HIV test that's 99% accurate, but has a 1% false positive rate, and you administer that HIV test to 100 million people, you're ultimately going to be telling, if the rate of HIV infection is actually very low, you're ultimately going to end up telling about 1 million people who don't have HIV that they have HIV, which is where these classifiers fail. And the open world versus closed world is another thing that you'll see studied and mentioned. There was a series of papers that did not really deal with both. And so what the distinction is, a closed world is the assumption that you know the list of pages that's being accessed. And where this would apply on the regular internet is, I know that, okay, I see that Wikipedia is being accessed. I know all the set of Wikipedia pages. And so that there should be no classification error or misclassification of strange things being in that data set because I know it's one of these pages. But on the other hand, the open world is where you might have an SSH tunnel that you're looking at, and you don't necessarily know what website is being accessed or if it's even web traffic at all. So there's that distinction is important to keep in mind. And the reason why I think this is important is a truly closed world, might not exist, and when you're actually outside of lab setting, things like varying implementations and settings for browser cache and the amount of memory devoted to the browser cache, depending on the user agent or platform, whether or not, what JavaScript is doing what in response to mouse movements or anything else that's going on the page, content that changes over time. Some studies actually found that if in just a couple of days, classifier accuracy just plummets on standard data sets just because the web changes enough over that period of time that everything starts getting misclassified if you don't keep your classifiers up to date with fresh training data. So what are you looking for if you're trying to evaluate or reproduce work or evaluate if a particular attack or defense is worth paying attention to? Well, these things are, the primary thing is either the Bayesian detection rate, which is also known as precision, and that is basically what tells you the effect of the base rate fallacy. So if you have a large world size, and you have a high false positive rate, the Bayesian detection rate will end up being low. And that's different than just the false positive rate itself, because what it's effectively telling you is the probability of you having a match given that your classifier said that it's a match for your class. This is a related metric is the third one, which is the precision receiver operating characteristic curve. That will be, again, sensitive to world size because when you're making that evaluation, you are doing it with respect to a set of classes and examples that you're classifying. You also have the receiver operating characteristic and the area under that curve, which is the trade-off between false positives and true positives in the data set. And similarly, interclass and intra and interclass variance, the rate at which your features vary and the rate at which your classes and the resources there are in them vary, is something that should be measured. So what is this, like another way to look at this, if you have a particular attack that is reporting a very high classification accuracy, a true positive rate, like almost 1, and then as the number of pages that it's trying to classify is increasing, they'll say that, oh, well, the false positive rate levels off no matter, as that number of pages grows. But even though the false positive rate is leveling off, the probability, because the world size is growing, the probability that you have a match given that your classifier says that you have a match is actually plummeting. And it becoming, as the world size grows, it becomes increasingly unlikely that information is actually worth anything. So the defenses that we've considered, I made a randomization of the pipeline in Firefox just as a sort of a straw man defense, just to get people to continue studying the problem. That had mixed results, possibly because of the uneven deployment of pipelining on the sites that were being studied, and like other factors that weren't clear. There's basically a long list of these. Most of these were rejected for the single reason that they either added excessive amounts of overhead or latency to the amount of to the traffic on the Tor network. The one that we ultimately settled on is this last one. We're working on an implementation of it right now, which is adaptive padding. Next. Now this defense we like it because it doesn't add any latency. Moreover, what it effectively does is shifts the distribution of your traffic towards a target distribution with minimal overhead. Basically, the way it's set up is you have a couple of state machines that react to traffic on each side of the connection, and there's what's called a burst state, which tells you whether or not you should send a padding packet in response or after receiving a non-padding packet. And if you do send a padding packet, then you move into the second state, and that state tells you the probability, or gives you a probability distribution of sending a padding packet after you just sent a padding packet. And there is a histogram associated with each state that allows you to define that probability distribution based on time. So it specifies effectively a delay distribution for sending those packets, and then there's a termination probability encoded in that histogram that tells you when to stop sending padding packets. Those histograms, in order to achieve the optimality and to shape the traffic towards the target distribution, those histograms have a set of tokens in them, and those tokens are removed whenever there is a padding or a non-padding packet that is sent. And basically, this is what provides the adaptive quality of adaptive padding, so that if your resources that are being sent match the distribution, very little padding is going to be sent, and if they don't match the distribution, that's when padding is going to be sent to try to make that set of those traffic patterns look more like your target distribution. So choosing those histograms is basically the key to optimizing the defense, so that they match basically optimally what your typical page load or largest page load looks like. The overhead of the defense is tunable anywhere between 0 and 60%. Again, because you're only sending traffic if the wire is quiet, there's no latency cost. You're not delaying any traffic. And here's in this graph, you can see the accuracy versus the overhead ratio of two different histogram distribution choices for those delay distributions. For the solid line, you can see that there you get a large benefit against that particular data set of pages with pretty much right away. With like as little as 5%, you get a very large increase or very large decrease in the accuracy, and then the slope changes until you get to about 25%, and then the slope changes again until you get to about somewhere around 66%. Then the defense simply stops providing any benefit in decreasing accuracy. And just for people who want to follow up on the set of attacks and defenses of the whole traffic analysis body of work, there's a selection of pretty useful papers to get started. I don't know if you can. I don't expect you to copy them down right now, but the slides are attached to the IETF work group page. I think that is pretty much it.
Thank you very much.
Thank you.
Questions? We have 10 minutes left for questions. Everybody's cold. I guess you're around for at least today and tomorrow?
I leave midday.
Okay. But like if people want to talk to you, they can catch up with you today. Okay, thank you very much. So as we have 10 minutes, I can actually go back to the chair slides and show you the slides that I missed in the beginning.
We meant to do that, really.
I have some, like, first of all, we have a next session right after the session in the same room. I said this already. But we also brought some stats for you.
So basically, we're just recognizing the people who've done reviews for the TSV area review team, and they're involved with a number of reviews that they've done. We're still adding people. We picked up, I think, 3 people who have specific expertise in RSVP protocol, and we got a review out of one of them. So we're really excited about continuing work there, and appreciate the triage team very much for their help with that. Yeah. So what do we want to say about our working groups?
Yeah, this is just like a quick update about what's happening. We have a few working groups that are not meeting, and we have the AQM working group, which is close to be closed. The last document of the AQM working group is the working group last call for that document, just not the working group, the IETF last call for that working group document just finished. So that will be closed very soon. And I think all the other groups are kind of processing nicely here. Thank you.
So we did have the in situ OAM work that's popped up in IPPM this morning. That's been to 4 other places that were not the right place for it to be, and it looks like they found a good home now, and we really appreciate that. Next slide. We did produce some documents in the last IETF cycle, and this is current as of 10 o'clock this morning, when the last approved announcement to be sent was actually put in the RFC editor queue. So we are getting work done, and we hope to do more work in the next IETF cycle. Anything else? Yep, cool.
Yeah, then we have a break, and see you after the break here again. Thank you.
Thank you all very much. Yeah, we were flying low. We are back in here, so I think I would just leave everything.
Hi.
Hallo. Ich muss einfach nur mal versuchen, ich habe deinen Namen gestern gelesen und da ich typisch Deutsch, dann habe ich die vorhin im Mikro gehört, das klingt auch typisch Deutsch, das wird sie wohl sein.
Das war kein Kompliment.
Nein. Super cool. Also, meins ist wesentlich häufiger. Yes.
Schreibt sich her?
Der Zufall.
Okay.
Mein Normaljob hat mit dem IETF zu tun, eigentlich die Storage Admin in Backend in Bayern. Aber ich habe die letzten 3 Jahre nebenbei in den Hand studiert und im Januar war ich in Australien und meinte dann eine Frau so, ja, das, was du machen willst, klingt cool, falls du IETF wissen wollte, mit dem müssen wir die wissen Bescheid. Jetzt bin ich hier auszufinden, mit wem ich überlegen muss. Und ich versuche, die ICMT nachdenken, gemäß dem RFC 508 und weiter funktioniert und ob so wie es umgesetzt wird, die Sicherheitslücken und Exploits, die dann wirklich sind, begünstigt oder ob die trotzdem funktionieren, wenn es so richtig implementiert wäre und was man dagegen tun kann. So Cover-Channel-Technik und so weiter. Problem ist, es liegt irgendwo zwischen Routing, Internet und Sicherheit und keiner weiß so richtig. Und 9 von 10 Leuten haben mir gesagt, weiß nicht.
Also ICT, ja, zum einen weltweit, zum anderen
Genau, wenn es funktioniert,